Hmm. Good morning, students. In yesterday class, we discussed the integrals of the type integral 0 to 2 pi f of cos theta sin theta d theta, that is integration around the unit circle. Now I am going to explaining the integrals of the type integrals of the type integrals of the type integral minus infinity to plus infinity f of x dx. This is second model in evaluation of real definite integrals. Integrals of the type minus infinity to plus infinity f of x dx using contour integration or by using Cauchy's residue theorem and that is also known as integration around the semicircle. Previous model is integration around the full circle, mod z equal to 1. Now I am going to explain the integrals around the semicircle. In this semicircle, first to draw the imaginary axis, real axis, and draw the semicircle. It varies from, for example, minus r to plus r. Then extend it 1 into infinity on right side, and left side it is extending to minus infinity. Here I, 2i, 3i, 4i, like that. In this case, we consider the poles of f of z only on imaginary axis. That means the f of z has no poles on the real axis. Such problems are only solved in this type. That means the f of z is having poles on the imaginary axis, not on the real axis. So mention I, 2i, 3i, 4i, etc. So in this case, directly consider integral over C f of z dz. Since we know integration over C f of z dz, that is equal to 2 pi into sum of the residues. This can be written as CR f of z dz plus integral minus r2 plus r f of x dx. What is CR? Here CR is circle mod z equal to r. So integration over C f of z dz is integral over CR f of z dz plus integration minus r2 plus r f of x dx by the help of the semicircle. This value is equal to 2 pi I into sum of the residues. At the poles. Sum of the residues at the poles inside C. By Cauchy's residue theorem. So in this case, directly consider integral over C f of z dz. That can be written as integration along CR f of z dz plus integration minus r to r f of x dx. This value is equal to 2 pi into sum of the residues at the interior poles or poles lies within the circle. That means the poles on the only imaginary axis. But here we want to evaluate integration minus infinity to plus infinity f of x dx. So apply limit on both sides as r tends to infinity. Limit r tends to infinity. Integration over C f of z dz is equal to limit r tends to infinity. Integration over CR f of z dz plus limit r tends to infinity minus r2 plus r f of x dx. Here we extend r to infinity in such a way that integral over CR f of z dz becomes 0. So we are extending r to infinity in such a way that integration over CR f of z dz becomes 0. That implies integral over C f of z dz is equal to integral minus infinity to plus infinity f of x dx. That is equal to 2 pi I into sum of the residues r1 plus r2 plus r3 and so on. Sum of the residues at the poles inside C. Since limit r tends to infinity, integral CR f of z dz is equal to 0. Then only we get the integration minus infinity to plus infinity f of x dx. This is called integral of the type minus infinity to plus infinity f of x dx. This is also known as integration along the semicircle. That here we have mentioned two conditions. First condition is f of z has no poles on the real axis and f of z has poles on the only positive imaginary axis, like I, 2i, 3i, 4i. Such problems are only solved in this type integration along the semicircle. Second condition is we are extending the r to infinity in such a way that limit r tends to infinity, integral over CR f of z dz equal to 0. Then only we can solve the integrations minus infinity to plus infinity f of x dx. In this case, directly consider integration over C f of z dz. F of z dz. That means every x by z and dx by dz. And minus infinity plus infinity is nothing but integration along the semicircle C. What is C? Mod z equal to r. Mod z equal to r and r tends to infinity. So directly consider integral over C f of z dz. But we know the value of this one. Integral over C f of z dz, that equal to 2 pi I into sum of the residues at the poles inside C. So directly consider integration over C f of z dz. Then calculate the poles of f of z by equating the denominator to 0. But the condition is the poles lies on only positive imaginary axis, not on the real axis. So calculate the poles and identify the poles of order. Then calculate the residues at the poles inside C only. Then integral over C f of z dz is equal to 2 pi into sum of the residues at the poles inside C. At the end, making r tends to infinity, we get the integral minus infinity to plus infinity f of x dx value. That procedure is called integrals of the type integration minus infinity to plus infinity f of x dx. But previous problem is integration along the unit circle. That means theta varies from 0 to 2 pi. Here minus infinity to plus infinity f of x dx. I am going to explaining the problems on integration around the semicircle, in which the first problem is evaluate integral minus infinity to plus infinity x square dx by x square plus 1 into x square plus 4 using residue theorem. Using residue theorem. And clearly observe this problem, it is integration along the semicircle, since it varies from minus infinity to plus infinity and in terms of x. So in such problems, directly consider integral over C z square by z square plus 1 into z square plus 4 dz. So what is f of z here? Z square by z square plus 1 into z square plus 4, where C is contour circle, where C is mod z equal to r, where C is mod z equal to r. That means first draw the circle. It is a semicircle, minus r2 plus r, then extending to plus infinity. It was extending to left side minus infinity. That is the circle. Here, that is the first step. next second step is the poles of f of z are z square plus 1 into z square plus 4 is equal to 0. That implies z square equal to minus 1 comma z square equal to minus 2i, z square equal to minus 4. So we get z equal to plus or minus I and z equal to plus or minus 2i. We get 4 poles, I, 2i, minus I, minus 2i. Among the poles, only I and 2i lies on the semicircle mod z equal to r. Minus I, minus 2i lies on the lower semicircle. But here we are integration along the upper half of the semicircle. So z equal to I and z equal to I are only lies I, comma 2i lies inside C. What is C? Mod z equal to R. And both are simple poles. This is the second step. What is the first step? Directly consider integral over C f of z dz, z square by z square plus 1, z square plus 4 dz. And then mention C mod z equal to R. And draw the semicircle minus R to plus R and extending to minus infinity to plus infinity. Then calculate the poles. Z square plus 1 into z square plus 4 equal to 0. We get 4 poles plus or minus I plus or minus 2i. Among the poles, only I, 2i lies within the upper half of the semicircle. Minus I, minus 2i lies in the lower half of the semicircle. So don't consider minus I and minus 2i within the C. Within the C, only I, 2i are there. So both are simple poles. Now calculate the residue at the I. Now next one is residue of f of z at I. Residue of f of z at z is equal to I. Here z equal to I is a simple pole. So its residue formula is limit z tends to I, z minus I into f of z. Z minus I into f of z. That equal to limit z tends to I, z minus I. What is f of z? Z square by z square plus 1. This z square plus 1 can be written as z plus I into z minus I into remaining value as it is z square plus 4. Here z minus I cancel, then that is I square by I plus I 2i and I square minus 1 plus 4. So its value is equal to, here I cancel, I by minus 1 plus 4 is 3 into 2 6, I by 6. This I and I cancel, I by 6. Next calculate residue of f of z at z equal to 2i. Residue of f of z at z is equal to 2i. It is also a simple pole. So limit z tends to 2i, z minus 2i into f of z. Z minus 2i into f of z. That is equal to limit z tends to 2i, z minus 2i into, what is f of z here? Z square by first term z square plus 1 as it is. Z square plus 4 can be written as z minus 2i into z plus 2i. Here z minus 2i cancel. Then replace z by 2i. 2i whole square means minus 4 by z square plus 1. Z square means 2i whole square, that is minus 4 plus 1 into z plus 2i, it will be 2i, 4i. 4 cancel. Minus 4 plus 1 is 3 and I minus means I square, I cancel. So it is I by 3. This 4 cancel. So remaining value I by 3. I by 3. Minus 1 means I square. So it is I by 3. Then calculate integral over c z square by z square plus 1 into z square plus 4. Minus 4 plus 1 means minus 3. So I by minus 3. I by minus 3. dz is equal to integration over c f of z dz is equal to 2 pi I into sum of the residues. What are the residues here? I by 6 minus I by 3. Minus I by 3. That equal to 2 pi I into, here LCM is 6. So it is I minus 2I by 6. That is equal to 2 by 6, 3. So pi I by 3 into I minus 2I minus I. This is equal to pi I by 3 into I minus 2I minus I. So it is equal to pi by 3. I into I square minus plus pi by 3. Therefore, integral minus infinity to plus infinity x square dx by x square plus 1 into x square plus 4 is also pi by 3, as making r tends to infinity, as making r tends to infinity. Once again, here evaluate minus infinity to plus infinity x square dx by x square plus 1 into x square plus 4 dx using residue theorem. Clearly observe this problem. It is integration around the semicircle from minus infinity to plus infinity. That is, we draw the semicircle from minus r to plus r and then extending. So circle is mod z equal to r. In this case, directly consider z square by z square plus 1 into z square plus 4. So f of z is z square plus z square by z square plus 1 into z square plus 4. The poles of f of z are z square plus 1 into z square plus 4 is 0. We get 4 poles, I minus I, 2I minus 2I. Among the poles, I, 2I lies inside the circle, upper half of the circle, remaining are lower half of the circle. So we have to calculate the residue at I and residue at 2I. And both are simple poles. So residue at I is limit z tends to I, z minus I into f of z. Z minus I into f of z, z square by z square plus 1 into z square plus 4. In first case, z square plus 1 can be written as z plus I into z minus I, since z minus I obtained from z square plus 1. So z plus I into z minus I, remaining z square plus 4. Here z minus I cancel and replace z by I, that is I by 6. Next, residue for the function f of z at z equal to I. It is also a simple pole. So limit z tends to 2I, z minus 2I into f of z. What is f of z? Z square by z square plus 1 into z square plus 4. But z minus 2I obtained from z square plus 4, that is z minus 2I into z plus 2I, and replace z by 2I, that is minus 4 by minus 4 plus 1 into 4, it is I by minus 3. So minus I by 3. Therefore, integration over c z square by z square plus 1 in z square plus 4 dz is, it is of the form integral over c f of z dz, that is equal to 2 pi into sum of the residues. Here we get two residues, one is I by 6, second one is minus I by 3. So I by 6 minus I by 3, that is 2 pi I into I minus 2I by 6, that equal to pi I by 3 into minus I into I square value minus 1. So we get pi by 3. So minus infinity to plus infinity, x square dx by x square plus 1 into x square plus 4 dx is also pi by 3, by making r tends to infinity. So then 0 to infinity means half of the this value. This is minus infinity to plus infinity. Minus infinity to plus infinity value pi by 3. Suppose the problem is 0 to infinity, that means it is 0. 0 to infinity means half of the whole value, as making r tends to infinity. Thank you.